Okay, from the last example in the previous video, example 7, we took a look at an integral right here, where after performing a u substitution, we were able to write it in a format that the integrand looks like a p function, a p integral, just like before, but our bounds, we didn't go on forever. So this integral was still an improper integral because our function, because our function here approached infinity. Its value became unbounded. It has an infinite discontinuity at u equals 0. So as u approaches 0, 1 over u squared approaches infinity. So it was still improper, but it didn't fit the format of our first kind of p integral. So we had to do this one by hand, and we found out that it diverges. So now we're going to have a theorem here that just sort of summarizes it. It's a very different, to compare and contrast it with the other kind of p integral. The other kind that we first learned about was from a to infinity of 1 over x to the p dx, and this did one of two things. It either diverged, and it diverged if p were less than or equal to 1, and it converged to a to the 1 minus p over p minus 1 if p were strictly bigger than 1. So if you compare and contrast these, you'll see some notable differences. So the 1 integral, this top one, here we have a function like this, and we are finding the area under the curve from some starting value x equals a all the way to infinity. That's the picture for that first one. I just realized that's off the page. There we go, a little bit better. So the second kind, this new one that we're learning about, this one is very different. Well, I wouldn't say very different, but it is different. 1 over x to the p, again, has the same sort of format, the same sort of, maybe not as, there you go, something like that. So still 1 over x to the p, but in this case, we are going from 0 and we're stopping at some a value. So no matter how you look at it, we're going, this area is sort of like flipped, almost like a reflection about this line. Like if you were to swap, this is the x-axis, but what if you were to, again, move this like up here, reflected about this line, swap your axes, then this area would kind of come here. So I would think of it like this. Really, think about this entire region here. Well, the one kind of integral just finds this half. The other kind of integral finds this half. All right. Sorry, I just want to erase this real quick. So the way I remember this is we either will be integrating over bounds that are infinitely long. So here, the actual domain of integration along the x-axis, we are integrating something that's infinitely long. Whereas here, our domain of integration isn't unbounded, it's bounded. It does not extend forever in one or both directions. But what does become infinitely large is not our domain, but the actual value of the function itself, its height. So how tall does this function go? That becomes infinite. So for me, I call this first kind of integral, I think of this as the big interval, because it's, unbounded. It's going all the way down the axis in one or possibly in both directions, depending on how your integral is written. And then this one down here, I think of this as the little interval, because our interval of integration is, compared to this one, it's the smaller one. It's bounded. It's not unbounded. Furthermore, oftentimes we are presented with such an integral and we want to know, does this integral converge or diverge? So does it converge? Yes or no? Well, if we want to, so let's answer that question for an integral of this type. A to infinity, the big interval kind. When do we have convergence? Well, we have it when p is bigger than 1. So in order to achieve convergence, and we have an integral of this form, we want the bigger value of p. We want big P. However, if we're presented with an integral of the other kind, where our interval of integration is bounded, it's not unbounded, it means we have the smaller or the little interval, when does this kind of integral converge? Well, it converges when p is less than 1. It's littler than 1. So for the little interval variety, we want little p. And that's how I remember this. Another thing that's important to note, it's subtle, but it is important, these expressions here are not exactly the same thing. You'll see in both cases the exponent is 1 minus p, but you'll see the denominator is different in these two cases. It's flipped. The reason for this is, let's take a look at this one down here, 1 minus p. This expression only makes sense when p is less than 1. So 1 minus p is in fact positive. If we had p minus 1, that would be, if p is less than 1, this would be negative. But this function lives above the x-axis. It lives above it. So the area has to be positive. So if you ever get this mixed up, just check to see, is your answer positive or not? This expression, does this denominator compute to a positive or negative number? If it computes to a negative, then you got the order mixed up. Okay. Let's take a look at this example 8. Again, here we can further, now we haven't done this in the past, but we can say this is the little interval. So this means we want, for convergence, so how about, let's write that differently. Let's say converges if p is less or littler than 1. Diverges otherwise. So our p value here is 2/3, which is less than 1. So this means the integral converges. To what value does it converge? Well, it converges to a to the 1 minus p over 1 minus p. Let's double check. Is that correct? If p is less than 1, then 1 minus something less than 1 has to be positive. So this is the right format here. So this, when we replace a and p in, our a value is 1. So this becomes 1 to the 1 minus 2/3 all over 1 minus 2/3. So this is 1 to the, well, doesn't really matter what this exponent is. If your base is 1, 1 raised to anything finite is 1. So this is 1. Our bottom is 1/3. So this is 3.